All right. Date today, Friday, March 26th. For your attendance, you guys are working on daily quiz number 17 on Gradescope. Make sure that you are. Somebody is not muted. You guys mute yourself. All right. So, make sure you turn in your daily quiz number 17 before midnight tonight. Homework 9 is due tonight as Tuesday of March 30th. So that's next class. I will be posting homework 10 early next week. We have exam 2 coming up also next week. So in 1 week from today, we are going to be working on exam 2. Studio 5 is due Wednesday of next week. And as I said, it has 3 tasks, and I want you guys to be working ahead of time. Don't leave things to the last minute. Studio 6 is pretty short. It's going to be, I will post it tomorrow, but it's a relatively straightforward studio. Okay, let us move on to our discussion about flip-flops. Hold on, there are some questions about are the exam logistics the same as the last exams? Absolutely, the same exact way, except the questions are going to be different. But I don't like to change exam logistics between exams because that can confuse students, and then things get lost in the shuffle. I don't know about difficulty. It's subjective difficulty. 44 multiple choice questions, 44 of them or 44 points worth of them. Oh, that's also a multiple choice. All right. All right, guys, let us come back to all right, I'll keep that in mind, Andrew. All right, let's come back to this. This is going to be also a fun exercise, and I would want you guys to participate. We are trying to design a new type of flip-flop, and I let you guys propose a name to this new flip-flop, and I'll also let you guys determine what this flip-flop does, right? So for example, if I paste a page before this, say add a new page before this, so generally we have seen that our drip drop flip-flop, okay, so I think that I like that drip drop flip-flop. DDFF. Nice. Not to be confused with flip flop flop. I think drip drop flip flop has a good vibe to it. I like that. Let's keep that. DD flip flop. Okay. Now this DD flip flop can do many things, but some of the things we could list here are setting a bit to a 1, or you might want to reset something to a 0, or you might want to hold or store, or you might want to toggle, right? These are the 4 kind of states that we have seen in the flip-flops so far. So let us see what we want our drip drop flip-flop to do. Actually, I don't want it to be drip drop now because it's DD. All right, we'll use D2 D1 then. So I'm going to make up my own characteristic table of the flip-flop. Now, because I cannot have DD, because that will make it confusing, I will use D0 D1. Randomize. All right, we've decided the name, you guys. I need other things that we need to discuss. D1 D0 are my inputs, and I want to find out what Q plus is going to be. The next state is going to be for this drip drop flip flop. By the way, we have made this name, so if you are watching the recording of this, there is no such flip-flop that you will find in a textbook called drip drop flip-flop. We have totally made this up. Okay, let's move forward. There can be 4 possibilities: 0, 0, 0, 1, 1, 0, 1, 1, right? And you can arbitrarily pick what you want your flip-flop to do when D1, D0 is 0, 0. So what do you want it to be? You have 4 options. Pick one for the first one, toggle. All right. So let us say we are toggling, which means what? Q plus is Q complement, right? Just the complement version of the past output. Next state, 0, 1. I'll let you guys decide what hold. All right, let's do hold here. Q plus equals Q. All right, next one, 1, 0. What do you want that to do? Reset. All right, let's do reset over here. And then just for the sake of completeness, you want to do last one. What about that? Set. All right. So we have, changed a few things around, and we have made up our own flip-flop. By the way, these could have repeated, right? Like you could have 2 states in which you store, or you don't have a reset state at all. It was completely made up. But by doing this, we are kind of shuffling the states of a JK flip-flop. That's all we are doing. But it's totally made up flip-flop. And the goal for this exercise is that you can actually use a completely arbitrary derived characteristic table and then make that flip-flop using some other type of flip-flop. Right? So we are going to try to design this DD flip-flop, and isn't this a latch technically? So we are going to make sure that we go from one state to the other when we see the active edge of a clock. That's when we are going to transition from one state to the other, which makes it a flip-flop as opposed to level. All right, so we have done this. You guys decided this, and then we are trying to design a DD flip-flop using a JK flip-flop. So I have entries in my next state table as D1, D0, the past output Q, and then the next state Q plus. And you guys determined Q plus already, right? Because you said toggle, store, reset, set. So let me just apply that to all the 8 entries in this next state table. For the first 2, you were toggle, right? So if it was a 0, it would become a 1. And then if it was a 1, it would become a 0. That's your toggle state. The first 2, D1, D0 are 0, 0. And the next 2 is what? Store. 0, 1, Q plus equals Q. So this would be a 0, this would be a 1. You are storing. After that, you are resetting and setting. So reset is independent of the past. Setting is independent of the past. That's right. So you got 2 zeros and then 2 ones. This is your DD flip-flop character next state table. Now you are trying to use a JK flip-flop to design this guy. So what I'll do is I am going to have to refer back to my JK flip-flop excitation table that we derived in the previous class. So I'll have to go back and take a look at that. And for those of you who were not there earlier in the previous class, we have derived it. And take a look at that. So we have J and K, right? So now I'm going to be focusing on strictly these entries. If I want those transitions from the previous to the new, what happened? All right. So 0 to a 1. What should I give at J and K to go from 0 to a 1? Andrew says 1, 1 because I am doing a toggle. But I could also be doing a set, right? Because Q plus is a 1. So I could either be doing a set or I could be doing a toggle. So toggle works, set works, both of them, right? So set is, which is jump, 1 0 for J and K, and then for toggle it is 1 1, right? Which means if you combine these two, you have to hold J at 1, and it doesn't matter what K is. Don't care. 1x, that's right. So for both those situations, you will get that transition to happen. All right, let me erase this. Now, if you do this for the entire 8 combinations, you would have filled up this, you would have used the excitation table of JK and filled up the table. Now, I don't want to spend all that time to keep writing the 2 states of all of these guys. I'm just going to go back and very conveniently look at the excitation table that we derived in the previous class, copy it from there, and then borrow it, paste it right here. So this is the one that we derived in the previous class. As you can see, 0 to a 1 is 1x. That's what we got. Now 1 to 0, what do we have? 1 to 0 is x1. Then 0 to a 0 is 0x. 1 to a 1 is x0. 0 to a 0, 0x. 1 to a 0, x1. 0 to a 1, 1x. 1 to a 1, x0. Right? So you're simply looking up the excitation table of a JK. We know how to derive it, but we don't really need to. We can use this as a reference. We have just used this as a reference. We have filled up all the entries in this table here. Now I don't need this anymore, so I can erase this off. Now my goal is going to be to write equations, logic expressions for J and K in terms of D1, D0, and Q. So what I'll do is I'll start off with a 3 variable K map for J, and I can do that later for the other one. So I've got 0 0 here, 0 1, 1 1, 1 0. This is D1 and D0 and Q. And then this is 0, this is 1. So I'm just writing the 3 variable K map for J over here. And then I'll do the same thing for K later on. Let's see. Now I need to fill in the entries. What do I have for J? 1x 0x, 1x 0x, 0x 1x, 0x 1x. All right, can you guys help me figure out the simplest SOP expression for J? Two groups of 2 ones. Bennett says D1 D0 or D1 complement D0 complement. That's perfect. So you guys are all on the right track. I'm going to just simplify this down to D0 exclusive NOR D1. Do you guys agree with that? I want you. Oh my gosh. Thank you. That's the simplified nicely. Yeah, I know. So, what if I disagree? Well, then we can have a discussion about why you disagree. Then you. All right. Do you disagree, Knife? All right. Okay. So we don't have a problem. Now I need to do that for the next one. You thought that was just something I say, huh? All right. It is next. We may get lucky with this, or it might not simplify very well. So let's see. X1, X0. X1, X0 again. Okay, so this is also some a little bit of interesting output that we have. Oh, by the way, I just need to make this 2 so that you guys can see the groups. All right, so what are we doing here? What is the simplest SOP expression for K? D0 complement. Okay, so let's try to point that out. 1 and 2. Right, that's it. That's the simplest group that you have. Q is changing. D0 is a 0. D1 is changing as well. So D0 complement. That's it. And that's your simplest SOP. Whoever chose these did a good job. You know it. All right. It could have been a little bit more interesting. Let's just leave it like, because none of these are kind of dependent on Q, right? Like Q cancelled out from here and here. So Q is not really playing a role. If it was, then it would add a little bit more interest to this arbitrarily designed no feedback right now outside, right? Inside there is, but outside of the JK flip-flop that we are going to use, there is no feedback. That is possible though. It just so happens that the flip-flop that we are designing doesn't need that. Okay, so we got those two expressions. So let's complete the design here. We have got this JK flip-flop, and it looks like we are designing a negative edge triggered JK flip-flop. Is it possible this has better characteristics than a JK flip-flop? No, it's the same characteristics as JK flip-flop. We are just shuffling the states. Now, what you really need is a D0, D1, like your DD flip-flop, right? And the expressions that we got were D0, D1 exclusive NOR, and then D0 complement, right? So I need an exclusive NOR gate. Let me try to make that over here. Did you know? Okay, and there, that's your exclusive NOR gate. And then we also need a NOT gate, right? That goes into my K input. All right. Then I've got D0, D1, and then one of them goes to the next one. So let's say this guy also goes to here. Oh, I need D1 here. I need D0 here. I've got everything is fine. And then I can also pull out the clock input, on which you have a square wave going in. That's it. That's your drip drop flip flop designed using a JK flip flop. So what I was saying is, you see, you could have had Q coming in to here, or Q complement coming in to here. That would have made it a little bit more interesting. But we don't have that situation play out over here. All right, questions about this example? And from the name to the characteristic table, you guys came up with the problems here. So the reason for this kind of a discussion is it should make you really, really comfortable with flip-flop conversions. You're not always going to get a standard convert a D into a T or convert a T into a JK. You're not necessarily going to get that kind of a standard conversion. Now I hope that you are ready to take up any flip-flop that you can design using one of the known flip-flops. Can we try one with Q feedback? I feel like I'm going to end up seeing this on the... You are absolutely going to see this on the test. If there are doubts, let me clear them up. You are absolutely going to see this on the test. Flip-flop conversion is Um, let's see. I'm going to point you to this one. There you go. So this is two such flip-flops, right? Like the flip-flop that you guys made up was D0 D1, your DD flip-flop. But you designed that using a known flip-flop. On one of the back exams from spring 2019, you are trying to design a MN flip-flop whose characteristic table is given to you using a UV flip-flop for which you are also given the characteristic table. So now you have completely like arbitrarily derived flip-flops and you are trying to derive one using the other. What is going to change? Well, the only thing that changes is you are going to have to use the characteristic table of the desired flip-flop, write that into your, that's right, you are going to have to essentially take this characteristic table of UV and then derive the excitation table of UV, right? That's what you're going to have to do. That's right. So I want you guys to kind of attempt this problem using the 3 steps that we talked about. What is that? This kind of... Hold on. What are you guys saying? My question was, is this better than, say, having Q feedback? Well, not necessarily. So better in terms of what? Like if you are having a feedback, then that simply means that the next state is going to be dependent on the current state, not just inside the flip-flops but also outside the flip-flops. But it's not necessarily better in any like anything special that's happening there. Now hold on, where are you guys at? Like I'm not able to follow the line of questioning here. All right, do you guys see the problem here? This is quiz 3 spring 2019. I want you guys to look at the back exam here. I will be posting the solutions, so you will get to verify your work, but you are essentially following the same things for a new flip-flops, right? So you have the characteristic table of the desired flip-flop, excitation table of the given flip-flop, K-maps, equations, sketch. Those are the things that are involved. Questions about this example? Okay. Now let's talk a little bit more about toggle flip-flops. So far what you have seen is a standard symbol for a T flip-flop, which is this guy, the top one. There is a toggle input that goes into the T input of the flip-flop. The clock source, the timing source, triggers the flip-flop. It is a positive edge trigger T flip-flop. And then you have two outputs, Q and Qn. Outputs are available in true and complemented forms. So that's one way of looking at a T flip-flop. Now, what if you want to have a slightly different approach towards toggling the outputs or not toggling the outputs? There is another way to do this, which is use an enable input. You see this? Use an enable input instead of the T input, and instead of clock going into the clocking source, your toggle input is going into the clocking source. This is sort of the same, the concept is similar to using a clock enable input that we have seen earlier, right? If you have no way to stop and start the clock, then you can use some external logic to enable and disable the clock input, as opposed to literally removing the clock source from your designs. This is something very similar. So what you're doing is you're using this enable input to enable the toggling function, and then every time you hit a positive edge on T input, your Q will flip. You will have a toggle operation going on. So you see the two differences here. The clock is now your T input, enable is your T input from earlier, right? So now let's see, it is best understood by looking at a timing diagram. So this is the new symbol that we have been talking about, and I have kind of said this a few times already, that toggle flip-flops are going to be very useful in the design of counters. So when you start designing counters, you will see that toggle flip-flops are going to be kind of your go-to flip-flops, because all counters do is toggle at different speeds, but there's toggling happening everywhere. So we are going to see toggle flip-flops play a crucial role in the design of counters. But you see, what is happening here? We are trying to compare our traditional T flip-flop symbol to this new one. You have an enable input, and if you look at this timing diagram here, you have different times at which you are enabling the flip-flop. Let me highlight them in green. The enable input is active high, right? So it is enabled here, enabled here, enabled here. Everywhere else it is disabled. Now, where is the what are you connecting to the clock input, the positive edge triggered? What is it responding to? What is it triggered by? It is triggered by the positive edge on the T, right? So you see, where is that happening? It is happening over here, positive edge, positive edge, positive edge. And at those times, enabled, disabled, enabled, right? So it is enabled here, it is going to toggle. It is disabled here, not going to toggle. And then again, it is enabled here, it is going to toggle. So you see, it is doing the same job for us, but now there is no such requirement for being periodic in terms of your enabled T inputs. This is basically, is the enable basically turning off the clock? That's right. That's exactly right. The enable, more precisely, is simply the clock enable. So you can say you're toggling here and you're toggling here. You're flipping only those two places, because at those times when you see a positive edge on the T input, those are the only times it is enabled. The other time it is disabled. So even if you see a positive edge on the T input, it is not going to toggle the output. All right. Now you have two more things over here. What are these? These are, you can think of these two designs in two steps. The first step is this: flip-flop conversion, right? So the first one, so let me number this. This is 1 here, this is 2 here. How do you get to 1? Well, you get to 1 by first deriving derive a T flip-flop using a D flip-flop. Have we done that before? I think we did. So let me just go back and check whether we did this in the previous class or not. Oh, there we go. We did this in the previous class, right? Deriving a T flip-flop using a D flip-flop. It involved a exclusive OR operation. We did that. Now, if I go back and take a look at the slide that we were talking about, so that exclusive OR is present right here. However, apart from that conversion, there's also another thing that is happening here. The same thing that was happening with this. Instead of T, you have enable. Instead of clock input, you have the T input. Instead of T, you have enable. Instead of clock, you have the T input. So those two combined, you are getting these designs. So this is the first one is deriving the T flip-flop using a D flip-flop with the enable, and the second one is deriving a T flip-flop using a JK flip-flop with the enable input. Questions about this? All right. We talked about this. We talked about. Let's do some examples. Let me work at making you guys very comfortable with flip flops. So this is a what type of flip flop is this? What type of flip flop are you going to classify this as? This is okay. So T, yeah, yes, but flip-flops are classified in two categories, right? There is a positive edge triggered, there is a negative edge triggered. So we are going to call this a negative edge triggered. Yeah. So it's a negative edge triggered toggle flip-flop. Perfect. You are given, in this example, you are given an arbitrary timing diagram for T, and you are also given a periodic signal for clock. How many times is Q how many times is it possible for Q to change in this example? Three times. And the reason for that is there are three negative edges of the clock. There are only three negative edges, right? Right. Now, it can only change at those 3 points. Now, let me talk about the timing parameters because we are going to need some assumptions. The way I have sketched the timing waveforms for T and clock, it is clear that I've assumed that the rise time is 0. Rise time is 0. It means that the wave, the signal is jumping from 0 to a 1 instantly, right? It's not practical, but that's an assumption that we are making. In reality, it is going to be a slow transition. Still pretty negligible, but we are assuming that it is 0. There is a jump there. The other assumption that I'm going to be making is that setup and hold times are being followed. Setup and hold times are satisfied. So we are not breaking any rules there. I'm going to assume that. And then I can assume that there is a very small propagation delay of say delta t through the T flip-flop. All right, so I've assumed these three things. Now I'm ready to sketch the output. So the first time Q should be evaluated is right here, right? Q at that point, will it toggle or will it not toggle? It will not toggle. Absolutely right. And it will not toggle because T is 0 at that negative edge. It should not toggle. But then I would need some information for the starting state of Q to be able to sketch it out. So I'm going to make my fourth assumption here. I'm going to assume that I always assume Q starts at 0. This time I want to start with 1. I'm going to assume that Q starts off with a 1. Right? So I'm assuming that the starting Q value is going to be 1. Otherwise, there was no way for me to find that out. And alright, so I'm starting to assume that that is a 1 there. So what is going to happen at the first negative edge? Is it going to stay the same, or is it going to go down? Stay the same, right? Because it is not toggling. Until then, it's not going to toggle. How about here? Will it go down? Yes, it is going to toggle because at the second negative edge of the clock, toggle input is 1. So that is going to trigger it to go to a low state, and the difference here between this and this is going to be delta t, right? There is a small, very small delay that we said, delta t. All right, how about the last one? It'll stay the same, right? No toggle. Yeah, it'll stay the same. That's it. That's your Q. Pretty simple. Sketching the output of a flip-flop by making certain assumptions about the timing parameters and a given symbol. So this was the given symbol, and we were able to sketch this out. Next, let's make it a little bit more interesting here. In the next example, we still have a negative edge triggered toggle flip-flop, and we have the Q output, the true form output, being connected back into the T input. And for this, I'm going to assume that my Q starts off at, say, a 0. Let's keep it simple here. Let's say this is starting at 0, right? So I'm going to make this a 0 to begin with. How many times can Q be triggered? Can this flip-flop be triggered? Why didn't you do decomplement? It's the same thing. If you get this, you will get that 3 times, right? All right. So let's see. Where are those times? Negative edge triggered, negative edge triggered, negative edge triggered. So you have 3 negative edge triggered things are over there, and I'm trying to sketch Q out, right? So until the first negative edge, what is going to be at Q? It is all going to be 0, right? It can never change until it is triggered. Now, what is going to happen at that time? Well, during this time, that 0 went to become a 1 there, and that 1 was fed back over here, right? Steady state at Q equals 1. That's right. So when you, at that moment, whatever that is, T1, say, we have a 1 input on the T, which means you are toggling, which also means that Q is now going to flip to a 1, right? All right, so Q after certain delay is going to it has jumped to a 1 after that delta T propagation delay through the toggle flip-flop. Next, because of that Q becoming 0, this is now changed, this is not changed, this is not changed. Now you have what? 1, 0, and a 0 there. Which T will always be 0. That's right. Which means you never toggle. Which means what Bennett said is steady state Q equals 1 is what we achieve. This guy will always be at 1 here. Doesn't matter now. You guys see that? So you can have situations like this where the output is going through some combinational logic and being connected back into the flip-flop here. All right. So hopefully that gives you guys some understanding about. Let's do another example. That gives me right. Let's do. All right. Hold up. I'm gonna have to write this problem out. I will use a D latch, a D flip-flop, say negative edge triggered and positive edge triggered. And then I will say this guy is not triggered, this guy is positive edge, this guy is negative edge triggered. And then I'm monitoring the Q and Q and Q, and I have, say, the same D connected all throughout. Same D. And then let us see, this is C, that's my clock, yeah, and then my clock goes there, goes there, goes there. All right. And then I have this at CLK. And then my outputs are, say, Q1 and Q2 and Q3. These are all D flip-flop latches and flip-flops, and we are only monitoring the true form of the output. All right. Why do you write C and not the arrow thing? Because I want this to be a comparison between a latch and a positive edge triggered flip-flop and a negative edge triggered D flip-flop. So I want to compare the three things provided the same inputs. So this is a latch, this is a flip-flop, and this is a flip-flop. Second Q should be Q2, right? Oh yeah, you're right. Okay, so you guys understand the problem here. We are connecting the same input D to all the sequential elements. We are triggering it. We are connecting the same timing source to all three timing inputs. One is a latch, so is responding to the level of the clock. The other two are positive and negative edge triggered. So it is responding to positive edge and negative edge of the same clock. And we are asked to sketch Q1, Q2, Q3, right? All right, now that you guys understand this, I'm going to need another page to do the exercise. So let's say D is over here. I'm gonna go some arbitrary and then clock. I'm just making it periodic. All right. So some arbitrarily decided D, some arbitrarily decided clock. Now let's try to sketch Q1. How can I sketch Q1? Well, Q1 is the output of the D latch. So the output of the D latch can change based on the level of the clock, and it has to be a 1. And if it is 1, here, Q1 will follow D, right? So it's going to be exactly the same as D, but for the first, until the first time it gets activated, what I'm going to say is, I really don't know what it is, right? So I really don't know what it is until that time. I could have assumed it, but in reality, I don't know what that is. It could be a 0, it could be a 1. But the time clock becomes a 1, now my D latch is going to follow the signal D. So it is 1 and then 0, right? So it's going to be 1 and 0 here. not too big, simply there and there and there. Now it's going to hold that until you actually go and enable it the second time. Now when you enable it the second time, it is going to follow D again. So it's going to jump up for a very short duration of time, and then it's going to go down and then stay there until you hit your third clocking time. So C equals 1 there. So there it's going to again try to follow D. Sometime it's low, then it goes high, then it stays at high, then it comes back down, and then it stays there. Do you guys see that? When clock is 1, Q1 is following D. Alright, so no questions for now. So I think that you guys are good with this. Let's try to sketch Q2. Q2 is an output of the positive edge triggered D flip-flop. Okay, so Q2, positive edge triggered. So let me erase this guy, this guy, this guy, and then mark up the positive edges of the clock. Right there and there and the third time, right? And at those times, Q should be following D, but only for those times. Until the first time, again, I don't know what it is. So technically, it could have been a 0, could have been a 1. So I'm just going to mark it as X. I don't know. But soon after clock goes from 0 to 1, soon at the time, just after that, and you're going to have to delay it by the propagation delay of the D flip-flop, D is a 1. So I know after that D is a 1. It will stay the same until your next positive edge. When you hit another next positive edge, D is again a 1. Alright. And when you hit the positive edge for the third time, D is a 0. So it's going to go back to 0 and stay there. Q3, output of the negative edge triggered D flip-flop. So things are sort of going to move here, right? There. To the negative edge of the clocks. And now Q3, I don't know what it is until this time. For certain, I cannot say. But at that time, D is a 0, all right? And then at that time, D is a 0, all right? And at that time, oh, so 0 all the way. So I hope that this example shows you guys clearly the differences between a D latch, a positive edge trigger D flip-flop, and a negative edge trigger D flip-flop. Questions here? All right. Now, as you are working through flip-flop conversions, anything really related to characteristic equations, characteristic tables, you are going to need a reference sheet, right? Like one place where you have all those characteristic equations and excitation tables and the next state tables of the standard flip-flops. So this is a slide which lists out the characteristic equations, and we have derived all of them earlier in the previous two classes for SR latch, flip-flop, D flip-flop, JK flip-flop, and a toggle flip-flop. How do you compute the next state Q plus given the inputs and the past output Q? Those are your characteristic equations. Next, the next state tables or the characteristic tables for SR, for JK, for D and T. Given the current state and its inputs, can you find the next state, Q plus? Again, we have discussed all of them earlier. This is just a summary of all those steps, all those tables. And then of course, this one is, in my opinion, the most critical reference sheet that you will need. So going into exam 2, I would highly recommend that you have this particular page as a resource available to you. This will come in very handy. So in one slide you have Q to Q plus. If you want that kind of transition from previous to the current to the new output, this is what the input you should give for SR, JK, T, and D. Some of these we have already derived. And then the equations are listed over here as well. So, going into exam 2, please have this handy. Now this last slide over here is simply sort of a statement summary of the design procedure. I'm not going to read this out right now because we have already done a couple of examples about this already. But this is big. If you needed this as a reference, here it is. If you are trying to convert a flip-flop to another flip-flop, then you first start off with trying to write the next state table of the desired flip-flop, right? Like that is critical. Desired flip-flop. And then you use the excitation table of the given flip-flop to fill out the inputs. So in the next one, you use the excitation table. Here is the excitation table of the given flip-flop. And then the final one is K-maps, draw the combinational network and all that. So we have done a few examples on this, but here is the statements capturing that. All right, I'm going to stop recording here.